Okay, ELC131, worksheet 21. This is part 2. What determines the primary side and the secondary side of a transformer? Transformers have two sides, most of them, and one's considered the primary, one's considered, well, they have two sides. They have a high voltage side and a low voltage side. So the primary side is where you connect the source to. So on an actual transformer with high and low voltage windings, the primary can either go to the low or the high, and what makes something the primary is where the power source is fed into the transformer. The secondary side of the transformer can either come off the high voltage or the low voltage windings, and it is actually the load. So the load on the transformer determines whether or not it's the secondary. So you can't look at the transformer and say, oh, this is the primary, that's the secondary. No, it has to go by how you connect it. Transformers have turns ratio, and the turns ratio is the voltage ratio. So if you put 24 in on the primary and you have a turns ratio of 3 to 1, then what you will get out is 1/3 on the secondary. Had the voltage ratio been 1 to 3, you would have gotten out 3 times as much as what you put in. So you have to go by the voltage on the primary and the turns ratio, and then you can come up with the secondary voltage. Most transformers are stamped with high voltage, low voltage, or the voltage ratio of the two sides, which is the same as the turns ratio. And they do that to make it easier. So if you buy a 480 to 120, you know that if you put 480 in, you'll get 120 out. And so they don't have a 4 to 1 ratio and make you do math, but they could. What determines the current in a transformer circuit? That is the load. The load always determines the current. If my resistance is infinite, I have an open circuit, I have no load. And if my resistance is a low enough value, I will get to what is considered the full load of a transformer. And so as my resistance or my load varies between infinity and some minimal value that represents the full load, then my current will be in a range between the maximum that a transformer can handle up to, well, down to 0. And that's one of the interesting things about transformer. You think more load is more resistance. It actually works the other way. More load is less resistance. How is the voltage regulation of a transformer calculated? You measure the voltage with no current. In other words, it's open, and you see what you get, and then you find the load that will give you the maximum current the transformer can handle, and that would be the full load voltage. And then it is no load minus full load divided by, it's either full load or no load, times 100. And that would give you your transformer regulation. It's something you can look up. Transformer regulation usually is important because transformers are pretty consistent, but they do have some internal resistance in their windings because they're made of coils, and coils have resistance in their windings. So as you flow more current, you'll actually see a voltage drop, and so you won't have as much voltage across the load. And so that's voltage regulation, just shows you how much drop you get. How are transformers rated? They're rated in something called volt amps, which is their voltage, either primary or secondary, times their current, primary, secondary. So, and those are the maximum values it can take. So if you have a 500 VA transformer and it's got 500 volts on it, then the maximum current is 1 amp because it's 500 times 1. If you have 250 volts on that transformer, then you can have up to 2 amps because 250 times 2 is 500. If you have 100 volts, you can have up to 5 amps. So transformers are rated in the product of the volts times amps. And whether you do the primary side or the secondary side, the volt amps are equal on primary side and secondary side. Not technically equal, but we consider them equal. There is actually a little loss on the secondary side, but we usually ignore it to make the problems easier. So now, 14. What is the VA of a system with 200 volts applied across a series circuit containing 200 ohms of resistance and 300 ohms of reactive? How much power is dissipated by a system with 200 volts applied across a series circuit containing 200 ohms and 300? So now, power problem. Now I started out doing VA, or I started out with the impedance, and I said the impedance is now a triangle. You have resistive and you have reactive parts. And so at the start of this problem, you have a resistive and you have a reactive part, and the impedance is the hypotenuse. And then the angle of the impedance is based on the two sides and the hypotenuse. It's a right triangle relationship. Your impedance triangle and your power triangle are similar triangles. Now, which means the angles are the same. So your impedance triangle and your power triangle, the angles are the same. This one I'll probably do in class because we need to do some work on it. And I need to show you all that. How to do it a couple different ways, probably with the spreadsheet. How many VARs are there in a system with 200 volts applied across a series circuit containing 200 ohms and 300 ohms reactive? So this one is similar to 14 because I'm using the same values. Yep. In the VARs, okay, in your power triangle, your horizontal part that corresponds with the resistance of the impedance triangle is your actual power. And the vertical part that corresponds with the reactance of your system is actually what we call the VARs. And then your hypotenuse, in the impedance triangle, we call it impedance, or Z, and we know it's the mix of resistance and reactance. That is actually your VA. And those are similar triangles, so it's actually quite easy. But 14 and 15, worksheet 21, I'll try and remember. If I don't, then y'all help me remember. So let's go on to 22. So we're going to draw the power circuit for the last problem, which we will do. And then find the polar impedances. 200, 300 ohm reactance. We can do that. And then we will do 22, 3, and then we'll look at the phase. Okay, so the last two on 21 and the first two on 22, I need to make sure I cover, or I need to set up better so I can cover it in a video. At what frequency would the capacitive reactance be equal to 0? We know the capacitive reactance formula, so if you make XC sub C equal to 0, what frequency is required? And then what frequency would cause the capacitive reactance to be infinitely large? The thing I'm wanting you to see is that it's opposite what happens with inductive reactance. So your zero frequency, or DC, your capacitive reactance is infinitely large, and then at very, very high frequencies your capacitive reactance is very, very small. And inductance goes the opposite way. Number 4 is just a problem where you are working coming up with the capacitive reactance and the inductive reactance, and you want the frequency where they are the same. So I'll give you a capacitor and an inductor, and since they cross, one inductive reactance goes up with frequency, capacitive reactance comes down with frequency. Since they cross, there's going to be a frequency where any two devices, the capacitor and the inductor, there's going to be a frequency where their reactances are equal. Okay, that is a special frequency, and that's called a resonant frequency. And then that's 4. For number 5, you can also, since capacitive reactance changes with frequency, you can find a frequency where it is equal to any resistor, and again, that is the corner frequency. Now we have the corner frequency for inductance, and you also have a corner frequency for capacitance. So that's an important concept in terms of where we're heading in terms of filters, which is really all we can really do with AC. I mean, you can do a bunch of resistive circuits and a bunch of, like we did in DC, and you can put capacitors and inductors in there, and you can do all that solving. But really the interesting parts are the resonance and the corner frequencies, because that's where neat stuff happens. Number 6, what is meant by the term impedance matching? Why is it important? How is it accomplished? So impedance matching, if you've got a radio in your car and you've got an amplifier and you've got speakers, you need to do something called impedance matching, because that will give you the most power out to your speakers, which would give you the biggest sound. Power is sound when it comes to speakers. Well, your amplifier has an impedance and your speakers have an impedance, and so one of the things that you can do with a transformer is you can transform the impedances, if you've got the right transformer, so that they match the source and the load impedances match, and then when you do that you get the most power out. You also do that in broadcasting with an antenna. You have to impedance match. Okay. So in an unmatched system with a source impedance of 8 ohms and a load impedance of 32 ohms, which device will have to dissipate the most heat? So if I've got 8 ohms in my source, 32 ohms in my load, and they are in series, 13.6 volt system, then I can talk about how much current it is, and then I can calculate the power. And then what happens if I've got 10 ohms and a load impedance of 4 ohms? Which device will have to dissipate the most heat? So I want you to show the values, and what you'll see is, since the resistors are not the same, the higher resistor will wind up dissipating the most heat, or the most power, will have the most power, which means it will have to dissipate the most heat. So this is to kind of go along with what's up here. And then what happens if I impedance match? Now we'll impedance match with a transformer, and we can make it perfect and get the most loads out. AC voltage levels can be varied by transformer. They are used to set the voltage levels to predictable values. 430 source needing to be 120 volts will need what ratio of turns? So I said the voltage ratio is equal to the turns ratio, so you can use the voltage ratio. Give me the ratio of turns. You can simplify it down to something to 1. however you want to do that. You just need to know that the voltage ratio and the turns ratio is the same, and if you know what you got and what you want, it's just a matter of finding the right transformer to get it, or building your own, which I don't recommend. A 24 volt AC source needs to supply 120 volts to a load. Will need what turns ratio? So now I'm going from a lower voltage to a higher voltage. So same thing, it's just a turns ratio. Alright. Given a 500 VA transformer with 120 volt primary, step down to 30 volts, supplying load of 15 ohms. What VA is the transformer using? Okay, so the 500 VA is its rating, but the load determines the current, and then the current times the voltage gives you the VA. And so what it's rated for and what it's using could be different. And so this is a matter of 30 volts, 15 ohms, so that's 2 amps, so this is about 60 VA. And so now what if I've got 500 ohms, 120, step down to 30 volts, supplying 5 ohms, what VA is the transformer using? And the higher the VA it's using, the greater the load, which actually means if you look at this problem, you'll see that the second example is using more VA than the first example, but the resistance is lower. So I'm trying to drive that point home. 500 VA transformer, 20 volts, stepping up to 100, supplying 50 ohms. What VA is it using? And again, another one. Now I'm stepping up the voltage. What VA is the transformer using? Higher VA means higher load, which means what for resistances. Okay. And then more general question, what determines how much VA a transformer is using? Then what is the purpose of the VA rating? So the load's going to determine how much it's actually using. The purpose of the VA rating is the limit to what that transformer can withstand. Okay? And transformers don't always go solely on VA, because you can take the transformer ratio and you can go with very small voltages and seemingly get very high currents to get to the VA that it's rated for, but sadly in the real world, transformers, in addition to being rated in VA, have a maximum current limits based on wire size. So the wire size that constructs the transformer limits the current to what the wire can handle. So you can have a 500 VA transformer with a 3 amp limit, and what's the greatest load that can be sourced at 24 volts? Okay, so 24 volts, 3 amps max, what, 72 VA? And so that would be limited based on the current rating, because the transformer will handle 500, but it only handles 3 amps. Okay, 22, and I'm going to go to 23 because I think there's a similar problem on this one. There we go. Now I've got a 500 VA transformer, 3 amp limited. What's the greatest load that can be sourced at 240 volts? So 240 volts times a little over 2 would put you at 5. So now this one would be VA limited based on the calculations. And so it's important to understand that when you're dealing with transformers. Okay, I'm going to stop here and call it 2122, and then I'll pick up 23 with the transmission lines. and then we'll get into low pass, high pass filters. We're actually going to use that corner frequency. Alright, I thank you for watching.